The measured capacitance of a reverse bias silicon Schottky diode is given by 1 by C squared is equal to 1 by C naught squared minus kV, where C naught is 1 puff and K is 2 picofarads to the power of minus 2 volt minus 1. V is the applied reverse bias voltage. The diode is uniformly doped N-type. Device area is given. Find the metal work function or a Schottky barrier height in the system. So now let's recall the Schottky diode. So in the reverse bias Schottky diode, right, it looks like a PN junction in the way the formula works. Remember, the Schottky diode is a majority carrier device, right? So the physics is different, but in modeling, the Schottky diode looks very similar to a PN junction diode. So the capacitance in the reverse bias Schottky diode can be written as A times square root of epsilon s nd into q divided by 2 into phi I minus Vi, where phi I is the built-in voltage of the Schottky diode, which is phi B, and Va is the applied voltage, right? So if I take the reciprocal on both sides and take the square on both sides, I get 1 by C squared is equal to 2 into phi I minus Va divided by q epsilon s nd a squared. In other words, 1 by C squared 2 phi I by q epsilon s nd a squared minus 2 by nd a squared into Va, right? So this can be written as 1 by C naught squared and this can be written as Kb, right? So that what you're seeing is that when I plot 1 by C squared versus voltage, I'm going to get a straight line whose x-intercept gives me the C naught and whose slope gives me the value of K, right? So you know how they're connected to physical quantities. You're asked to find the metal work function in the system, right? Be given the area. So let's first start with phi I. Right? So to find phi I, what do I need to do? So therefore I have that 1 by C naught squared is 2 phi I by q epsilon s nd a squared, and my K is given by 2 by q epsilon s nd a squared. So therefore if I want to find phi I, or the built-in voltage of the diode, that is nothing going to be 1 by C naught squared times K, right? I divide this equation by this equation. In other words, that is going to be equal to 1 by 1 puff the whole squared times 2 into picofarad minus 2 volt minus 1, and this gives us 0.5 volts. So the built-in voltage of this Schottky bias or Schottky diode is half a volt, right? Now we need to find, I want to find the barrier height, right? And the barrier height, if you look at the built-in voltage of the Schottky diode, it depends on the barrier height of the system and the doping concentration in the semiconductor. So now I know the built-in voltage. I need to now estimate what phi s is, and once I know phi s, then I can find out what the barrier height is. So to know phi s, I need to know the doping concentration system, right? So therefore, once I know A is given to be 10 power minus 4 per centimeter squared, I know K is given to be 2 by q epsilon s nd a squared. That is given by 2 divided by 1.6 into 10 power minus 19 into 11.8 into 8.85, 10 power minus 14 into nd into 10 power minus 4 the whole squared, right? And this is equal to 2 into 1 into 10 power minus 12 the whole squared, right? Remember, I'm talking in SI units, so this K was given to be 2 PF minus 2 volt minus 1, right? So if I want to convert it to SI, I need to multiply by 1 into 10 power minus 12. So if I solve this equation, I'm going to get my ND to be 5.98 into 10 power 14 per centimeter cube. So this is the doping concentration in the semiconductor side of the Schottky bias or Schottky diode, right? Now I need to find phi s, right? So remember, this is EC, EV, this is your EI. It's an N-type junction, so your Fermi level is going to write somewhere here, right? So if I want to find the Fermi level, now I know Ni. So what I can do is I can write my Fermi level in the semiconductor to be either the electron affinity plus kT by Q ln of Nc by Nd. Remember, this is the distance between EC and EF. Or I can start from EI and come back as ln kT by Q Nd by Ni. Right? So I can measure off this. And so I know Ni, so I can go with this. So this is 4.55 minus kT by Q ln of 5.98 into 10 power 14 by 1.5 into 10 power 10. Right? So this works out to 4.28 electron volts. Right? So I know that the phi s is 4.28 volts. Remember, it's a Schottky diode, right? So Schottky diode means it's going to have something of this format, right? Which means that this barrier height, this is what we are talking is phi I. So if I want to find the barrier height is going to be, or the metal work function, the metal work function is going to be equal to 4.28 plus 0.5 or 4.78 electron volts, right? So phi b is going to be equal to 0.5, and if I look at the metal work function, the metal work function I use has a value of 4.78 electron volts. It's going to be like closer to the valence band of silicon and hence causing a Schottky diode with n-doped silicon. Moving on to the next question. A MOS capacitor is known to have a phi ms not equal to 0, QF not equal to 0 and a QM or mobile electron charge distributed through the oxide and a significant number of donor-like interface states. The CV of the device is shown below. For each of the cases listed below and taken separately, sketch the expected CV of the device superimposed on the original CV. Right? So let's start with this. So the first part is, let's first draw the original CV. So the original CV looks something like this. I have VGB, I have capacitance. This is my Cox. So the VFB is negative and your VT is here. This is Cox. Right? So this is an N-type substrate, right? And you have basically an inversion happening when you have a negative voltage on the gate. So first part says that an anneal is performed that totally eliminates interface states, right? So now if I think about interface states, what are interface states doing? Interface states basically spread out the CV. So what's going to happen is, if I do an anneal which removes the interface states, I'm basically going to create a CV that looks straighter in this way. So it's going to change the VT of the device and it's going to make the CV appear straighter, right? So if I remove the interface traps, this is how my CV is going to look like. The second question is, what happens if I remove QF completely? So if I do an anneal which removes QF completely, so again let's do that. Again, this is my original CV. Now if I remove, so what does QF do? QF, so delta VT is equal to minus QF by Cox, right? So having a fixed charge, which is normally a positive charge, reduces the VT. Or in other words, in the PMOS, it makes the VT more negative. So if I remove this fixed charge, then essentially what's going to happen is my curve is going to shift towards the positive side. And how much it shifts by depends on what this amount of fixed charge is. So if I do an anneal which eliminates the QF or the fixed charge, then essentially my CV shifts towards the positive x-axis and it's a parallel shift. And this parallel shift is determined by what the effective QF was when the initial capacitor was made. Now let's go to third part of the question, which again asks, a gettering is performed so that 10% of the mobile ions from the top of the oxide are eliminated. So remember, the oxide has a bunch of charge, right? So this is your gate, this is your silicon, and you have oxide charge, mobile charge present all over, be it positive or negative, right? Now, if you're reducing this charge, right, essentially what this means is you're reducing the net oxide charge in the system. So depending on whether it's a positive or a negative mobile ions, you will move the CV curve either in the positive X or the negative X direction. So generally the mobile ions are sodium or potassium, so they are positively charged. So if I'm removing 10% of them, it just means that I'm going to shift my curve again towards the left. It's like the fixed charge. Only thing is that the fixed charge change is larger because it is right at the interface. In the case of mobile charge, it can be anywhere. So this delta is going to be minimal. So again, the curve moves to the along the positive x direction. The amount it moves depends on how much of the charge is eliminated. The next question asks what happens if the metal gate is changed from aluminum to copper, which has a higher work function. So if the aluminum, so remember aluminum, this is a PMOS, right? Or it's an N-type substrate. So if I'm now going to, and remember what is happening in inversion, the bands are moving such that the surface gets inverted, right? So therefore, if I'm going to convert aluminum gate to copper, which is a high work function metal, it essentially means that I'm making it easier for the electrons to be inverted or the surface to be inverted, because at the onset itself I have a larger field because copper is going to be further down in the band gap compared. So for example, what I'm trying to say is this is EC, this is EV, right? Aluminum would be somewhere here, copper would be somewhere here. So if I start off with copper, right at when the bands are formed, that is when no voltage is applied, there's already a large field between the two. So therefore it's going to be easier to invert the surface. So what's going to happen is that when I move from copper to aluminum to copper, I'm going to have again a parallel shift in the CV, and this shift is going to be given by the difference in the work functions between the copper and the aluminum. So if I were to replace it with another metal, say which has an even higher work function, then the shift is going to be more. And finally, the last question asks what happens if the doping concentration increases. Right? So we know that if the doping concentration increases, what's going to happen is 1, your VT is going to go up, 2, your CFB is going to go up slightly because of the fact that your FIMS is going to change, and 3, your Cmin is also going to go up because of the fact that you have higher doping, so the depletion width is minimum. So therefore you're going to have something which looks like this. The VT again goes up, right? So you see a change here, you see a change here. So the VT increases, becomes more negative, and the Cmin increases because of the higher doping. Right? So again, understanding the CV is very important, and understand the impact. Remember, at all times, doping is going to make the CV less different between accumulation and inversion, whereas all the reduction of charges basically moves the CV depending on whether charges are positive or charges are negative. Let's move to the next question. The CHF by Cox for a MOS cap is given below. Now consider half another MOS cap with the same Cox dimensions but with positive charge in one half of the gate and the other half with no charge. Assume that the flat band of the contaminated half of the whole device's VFP is -2. Now draw the expected CV of the new structure on the same graph, right? So let's think about what's happening in this device. So suppose I have a new device, right? And this is my oxide, this is my gate, and this is my silicon. Now I only have positive charges in this half of the gate, right? So if I look between the gate node and the substrate node, I can think of this as two capacitors, each of half the area, right? So this is some C1 capacitor, this is C2 capacitor, this is CA by 2, this is CA by 2. The difference is that the VT of this is going to be different than the VT of this because of the lower flatband voltage that I have, right? And so therefore what's going to happen is, if you think about, if I were to just have this alone, right? So let's draw the CV graph. So in the first CV, I have something which looks like this, right? This is without the flat band. Now with a flat band shift of -2, I actually have, so if I have these two devices separately, this would be the device with the flat band shift and this would be the original device. Now what's going to happen is, if you now think about, remember you have these two capacitors in parallel. So when capacitors in parallel, the C total is given by C1 plus C2. So at all times I'm going to have these two capacitors add up, right? So basically think about it as essentially thinking of two curves, one curve this way, the other curve, as I said, in the green, and you sum them up together, right? So what's going to happen is, you're going to have, if I now draw it in red, you're going to have a sum here, and then it begins to fall, then again a flat, and then it begins to fall, right? So you're going to have two steps in the CV, primarily because one CV starts off earlier and then the second CV catches on, and eventually you're looking at a CV curve which looks something like this. So again, there's nothing complicated, just remember as to what the flat band does. Now if the charges were moving or if the doping had changed, things would have looked different. But again, we are considering as a purely 1D problem. So when you look at it as a purely 1D problem, then you essentially can think of this as two different devices which are connected in parallel, and then you can go about analyzing them separately. Okay, so going to the next question. Shown as a solid line in CV characteristics of an ideal MOS cap. The dashed line is CV characteristic of a MOS CV which is identical in every way to the ideal MOS cap, except that it has a fixed charge at the silicon-silicon dioxide interface. The oxide thickness is 0.1 micron. 1. Is the semiconductor N-type or P-type? Are they high frequency or low frequency characteristics? Justify your answer. 2. What is the gate area of the MOS capacitor? 3. What is the estimated value of the fixed charge? Specify the charge and the sign. And 4. Suppose the aluminum Ti gate metal in the ideal MOS cap is replaced with gold, which is 5 electron volts. What is the new flatband voltage of the MOS cap, assuming VFB is 0 in the ideal case? So first things first, is it an N-type or a P-type semiconductor? Obviously, given the fact that when you apply a positive voltage, right? So what do you have? When you apply a positive voltage, it goes into inversion, indicating that we are creating in electrons in the interface, and so therefore this is a NMOS like of thing. So it's a P-type substrate, right, with N electrons in the inversion layer. Are they high frequency or low frequency? They are high frequency characteristics because we see that the Cmin is reduced. In inversion, the capacitance doesn't come up to Cox. Now, second question asked is, what is the gate area of the MOS capacitor? So if you go back and look at the CV, you see that the C accumulation is 100 picofarads, right? And so therefore we have that A epsilon by Tox, right? Epsilon ox by Tox is the capacitance per unit area. A times that is the net capacitance of the structure is 100 picofarads. And so therefore I need to find area. So I have 100 into 10 power minus 12 is equal to A times 3.9 into 8.85 into 10 power minus 14. And I'm given that the oxide thickness is 0.1 micron, so that is 0.1 into 10 power minus 4. Right? And so this gives you an area of 2.897 into 10 power minus 3 centimeters squared. Right? I can also calculate the Cox per unit area. Cox per unit area is epsilon ox by Tox, and this is just 3.9 into 8.85 to 10 power minus 14 by 0.1 into 10 power minus 4, and this works out to 3.452 into 10 power minus 8 farads per centimeter squared. Right? So that's the oxide capacitance per unit area. Now you're asked what is the estimated value of the fixed charge. So what you see is when fixed charge comes in this structure, you see that the CV characteristics shift along the positive x-axis. Or in other words, Vt increases. So remember, delta Vt is minus Qf by Cox, right? So now what's happening in this case is because the Vt is increasing because of fixed oxide charges, it means that the fixed oxide charges are actually negative, right? Obviously, in silicon, most of the time the fixed charges are positive, but in this case, we see that the fixed charge is negative. And how do you calculate the quantity? So the amount of fixed charge is just given by Cox times delta VFB, right? And I'll just take the modulus because I know that the charge is going to be a negative charge. So I'm going to have 3.452 into 10 power minus 8, and the change in the flatband voltage is 1 volt. So it's 3.452 into 10 power minus 8 coulombs per centimeter squared. And so if I want to convert it to a number, the total amount of charge is going to be Qf divided by the electronic charge. So 3.452 into 10 power minus 8 by 1.6 into 10 power minus 19, which gives you 2.156 into 10 power 11 per centimeter squared, right? So this is going to be the charge density that I have per centimeter squared of the surface. So the last question says that what happens if the work function of the metal, which was initially 4.1 electron volts and that had a VFB of 0, changed to aluminum, which is 5.0 electron volts? What would the VFB be? So new work function is 0.9 volts higher, and so therefore what's going to happen is your delta VFB is just your delta phi m, and your delta phi m essentially becomes 0.9 volts. So the curve again shifts towards the positive axis and it gives a higher Vt of 0.9 volts. So again, understanding the CV curve becomes critical. Once you understand the CV, then you can start extracting numbers from the same. Let's move on to the next question. The CV characteristic exhibited by an ideal MOS cap is displayed below. Is the semiconductor doped N or P type? Indicate how you arrived at the answer. Draw the MOS cap energy band diagram corresponding to point 2. Band diagrams will include all three materials and should be drawn to scale. Draw the charge profile in the MOS cap corresponding to point 1. And if the area of the MOS cap is 30 mm squared, what is the oxide thickness? Okay. So again, the first thing is you see that the inversion is when the applied voltage is positive. So that means that we're creating electrons in inversion. So which means that the doping type is P type. So part A is going to be that the doping is P type. Now point 1 indicates when the MOS cap is in accumulation, and point 2 indicates when the MOS cap is in inversion. So you're asked to draw the band diagram when in inversion. The band diagram in inversion is going to look, you can refer to the videos, it's going to look something like this, where you have the Fermi level, you have inversion happening, so which means that your EI deep inside the semiconductor is P type, at the surface it becomes N type, your bands bend in such a way, so that's your EC, that's your EV, right? This is your EF in the semiconductor, and this is going to be your VG. So this delta between EF and this EFM is essentially the applied voltage that you've applied to get the MOS cap into inversion. The third says what should the charge profile in the MOS cap be in point 1. So point 1 was in accumulation. Accumulation, this is a P-type semiconductor. So therefore that means that accumulation means you have holes created. So if I plot the charge density, this is my oxide, this is my metal, this is my semiconductor. The semiconductor is accumulated, it's P-type, so I have holes. So if this is my charge, I have holes. So this is my N accumulation, which are holes. And to counter that, I'm going to develop a negative charge in the metal, and this is going to be my negative charge, which is going to compensate for the whole charge in accumulation. Last question is to find the oxide thickness. So again, here your C accumulation is 100 picofarads, right? And you're given an area of 30 mm squared. So again, your T ox is nothing but A into epsilon ox by C ox, which is A is 30 mm squared, so 30 into 10 power minus 1 squared into 3.9 into 8.85 into 10 power minus 14 divided by C ox, which is 100 into 10 power minus 12, and this gives you 1.035 into 10 power minus 3 centimeter or 10.35 micron. So that's going to be the oxide thickness for this MOS capacitor. Let's go on to the next question. Given an ideal silicon dioxide MOS capacitor maintained at room temperature with an oxide thickness of 50 nanometers, a p-type substrate with a doping concentration of 5 into 10 power 15 per centimeter cube and a gate area of 50 mm squared. A. Determine the maximum capacitance in the CV characteristics. 2. Determine the minimum capacitance in the high frequency CV characteristic. 3. Determine the VT of the device. D. Draw the energy band diagram. And 5. Sketch the high frequency characteristics to scale with significant capacitances and the voltages identified. So what are we given? We are basically given it's an ideal silicon dioxide capacitor. With ideal I mean is your phi mass is 0, right, or VFP is 0. You're given an oxide thickness of 50 nanometers, a p-type doping concentration of 5 into 10 power 15 per centimeter cube, and an area of 50 mm squared. So the first question was the maximum capacitance. The maximum capacitance is going to happen in accumulation, right? And it's going to be given by A into epsilon ox by tox, right? And that's basically 50 into 10 power minus 2 into 3.9 minus 14 divided by tox, and tox is 50 nanometers, so 15 to 10 power minus 7, and this works out to 34.52 nanofarads. So this is the maximum capacitance that the structure will offer when I put it in a tester. Now next question to ask is, what is the minimum capacitance, right? So if you remember the CV looks something like this. I have accumulation and I'm going to go into depletion, right? So this is my C and this is my C. So this is my maximum capacitance, which happens in accumulation. It's given by C ox. The minimum capacitance is basically C ox parallel to C depletion, right? So if you think about the equivalent circuit, this is how it looks like. I have a C ox and I have a depletion capacitance because of the doping concentration in the substrate. So I need to first find C depletion, and then I can find out what the C min is. So I can write my C min as C ox into C depletion by C ox plus C depletion. Now C ox is something we calculated. We need to calculate C depletion, right? And C depletion is nothing but epsilon silicon divided by XD max, or the maximum depletion width. And the maximum depletion width is given by 2 epsilon silicon times 2 phi f, because that's the voltage that is built in for inversion. The surface has the same doping concentration as the bulk but an opposite under the square root, right? So this is XT max. So therefore if I look at C depletion, my C depletion can be written as square root of epsilon Si into Q times Na divided by 4 phi f. Now I need to find phi f. My phi f is nothing but the distance of the formula from the intrinsic level. So it's given by phi f as kT upon Q ln Na by Ni. which in our case is going to be 0.0259. Ln Na is 5 into 10 power 15 by 1.5 into 10 power 10, and this is 0.2877 volts. And therefore your C depletion is nothing but square root of 11.8 into 8.85 minus 14 into 1.6, 10 power minus 19 into 5 into 10 power 15 divided by 4 into 0.2877, and this works out to 12.06 nanofarad per centimeter squared. Remember, I'm not invoked area in here, right? So now the area is 50 mm squared. So therefore my C depletion is actually 12.06 nanofarad into 50 into 10 power minus 2, which is 6.03 nanofarad. And therefore my minimum capacitance Cmin is nothing but, so I have this, right? I have a 34 point, what was the number? 34.52 nanofarads, which is your Cox, and a C depletion of 6.03 nanofarad. And so if you have connected two capacitors in series, the smaller one is going to dominate. So therefore this is going to be 6.03 into 34.52 divided by 6.03 plus 34.52, which works out to 5.133 nanofarad. Right? So that is going to be the minimum capacitance that is going to appear in this system. Part C of the question asks what Vt of the device is, and Vt is nothing but Vox plus Vs. Right? Vs in our case is the total depletion drop in the depletion, maximum depletion width, which is 2 phi f, which in our case is going to be 2 into 0.2877, which is 0.5754, right? So that's your voltage drop in the semiconductor. The voltage drop in the oxide is nothing but the charge dropped created in the across the oxide divided by the voltage. So Vox is nothing but Qs by Cox, right? Which is nothing but square root of 2 epsilon Qna into 2 phi f. So this is the net charge divided by Cox. So you can plug in the values. 2 into 11.8, 8.85, 10 power minus 14, 1.6 into 10 power minus 19, to 5 into 10 power 15 into 0.5754 divided by Cox, which is nothing but 34.52 into 10 power minus 9. Now this is the Cox of a 50 mm squared. This Cox, remember, is capacitance per centimeter squared. So this divided by 15 to 10 power minus 2, which is 0.2008 volts. Right? So that's the drop in the oxide. I know the drop in the semiconductor, and therefore my Vt, remember, it's an ideal diode, so phi ms is 0. So therefore my Vt is given by 0.5754 plus 0.2008, or your Vt is actually 0.7754 volts. Right? So that is the threshold voltage of this MOS cap. You're asked to draw the energy band diagram to scale. So that can be drawn at Vt by drawing the difference in the various areas. And if I'm going to actually plot the CV is going to look something like this. I have two levels, a maximum level of 34.52 nanofarads, a minimum level of 5.133 nanofarads, right? Now here the VFB is roughly 0 because phi ms is 0. So my CV is going to look something like this. Far away from Vt, my CV is going to hit this min and max, and then I can roughly approximate it to something like this, right? So this is going to be the CV of this device, roughly drawn to scale. Let's move to the next question. At room temperature, the low frequency capacitance voltage relationship measured between the gate and the substrate of a MOS cap is shown. The gate of this device is 20 micron by 100 micron. Use the data to answer the following questions. 1. What is the threshold voltage of the structure? 2. What is the flatband voltage of the structure? You can neglect the dipole length in this structure. 3. What is the thickness of the insulating silicon dioxide? D. Identify the type of doping, whether it's N or P type. E. What is the doping concentration in the substrate? And F. What is the work function of the metal used in the structure? So now let's start first with the threshold voltage. So in the threshold voltage, you see that the voltage comes, or the CV comes up. First of all, this looks like a low frequency characteristics with inversion happening when the voltage is negative. So therefore this is a PMOS cap. In other words, holes are created in inversion, which means it's an N-type substrate. Now the threshold voltage of the device is when the C comes up. So that is roughly going to be minus 1 volt. Right? So that is going to be the threshold. You can read it off the CV. You're asked to find what is the flatband voltage of the device. The flatband voltage is when the capacitance actually starts reducing as it leaves accumulation, and that is pointed in the figure. So you can see flatband voltage is plus 0.8 volts. Right? The third question is, what is the thickness of the insulating silicon dioxide? So again here you see that the accumulation capacitance is 2 picofarad. The area of the structure is 20 micron by 100 micron. And so therefore I can write my Tox as A times epsilon ox by C ox, right? So A is 20 into 10 power minus 4 into 100 into 10 power minus 4 into 3.9 into 8.85, 10 power minus 14, divided by Cox, which is 2 into 10 power minus 12. And this, if you work out, it works out to 34.51 nanometers. Right? So that is the oxide thickness in the system. We already said that the doping type is going to be N-type because this is a PMOS cap. Now next thing you have to identify is the doping concentration of the substrate. So to find the doping concentration of the substrate, remember the only part of the MOS cap which depends on doping is Cmin, right? Because that's where you see the depletion width of the structure. So if you look at Cmin here, you see that Cmin in this device is equal to 0.8 picofarads. Cox of this device is 2 picofarad, right? So again, like previously, we need to find C depletion, right? And this C depletion, so we know that Cmin is equal to C depletion and Cox connected in series. So therefore, if I know Cmin, if I know Cox, I can calculate the C depletion. This C depletion is 1.33 picofarad, right? And now this C depletion is a function of the doping concentration, right? So once I know C depletion, then I can calculate the doping concentration. How do we do that? So this is C depletion for the capacitor. So C depletion per unit area is 1.33 picofarad divided by 20 micron divided by 20 times 100 micron, right? And this works out to 6.665 into 10 power minus 8 farads per centimeter squared. So this is the capacitance, right? And we know that this C depletion is nothing but epsilon silicon by XD max. So this gives us XD max as epsilon S by C dep, which is 11.8 into 8.85, 10 power minus 14, divided by C dep, which is 6.65 into 10 power minus 8. And this works out to 0.1567 microns, right? So this is my XT max, Now, we know XD max is nothing but 2 epsilon s into 2 phi f divided by q times nd. And this phi f is kt upon q ln nd by ni. Right? So now here you know XD max and you know everything else. You need to find nd. So remember, phi f is a function of nd. So this, if I plug in the values, what do I get? I get 0.1567 into 10 power minus 4 should be 2 times, I'm pulling the 2 out, square root of epsilon s into phi f ln of nd by 1.5 into 10 power 10 divided by 1.6 into 10 power minus 19 nd. Right? In other words, if I were to collect all the nd terms together, I get nd divided by ln of nd by 1.5 into 10 power 10 should be 2.753 into 10 power 15. Right, now this is a translated equation. So easiest way to solve this is guess. So you see nd number, so you can start plugging in values of nd and calculating this expression. Right, it's 10 power 15, so start with 10 power 15, 5 times 10 power 15, so on and so forth, and keep guessing. So roughly what you get is, you get that nd is going to be roughly equal to 4.1 into 10 power 16 per centimeter cube. So that is the doping concentration of the substrate, right? So it's going to come by trial and error. And so once you know nd, your phi f can be calculated as kt by q ln nd by ni, which is 0.0259 ln 4.1 into 10 power 16 by 1.5 into 10 power 10, which works out to 0.384 electron volts. Right? So therefore my phi s, remember this is nd, so I have to, if I want to find phi s, which is nothing but EC minus EF, that is 4.55 minus 0.384, which is 4.216 electron volts. Right? Now in this case here, the flat band voltage we read off the figure is 0.8 volts, right? And this flat band voltage is nothing but phi s or phi m minus phi s. So therefore the work function of the metal is nothing but phi s plus the flat band voltage. So that is going to be 4.216 plus 0.8, which is 5.016 electron volts, right? So that is the work function of the metal. So you see that the CV characteristics are very useful. A lot of useful information can be collected off the CV characteristics if you look at it carefully and if you're able to extract the values from the same. Okay. Moving on to the next question. A researcher fabricates two MOS capacitors which are identical except for different oxide thicknesses. Specifically, TOX1 is 50 nanometers and TOX2 is 100 nanometers. The devices are free of mobile chargers and interface traps. However, the fixed charge QF and the phi s are both non-zero. Device 1 exhibits a flat band voltage of -2 and device 2 exhibits a flat band voltage of -3 volts. Determine both the phi s and QF. So this is a very useful technique to measure QF in processes. And basically what we do is we create MOS CVs with varying thicknesses and then we plot them to find the value of flat band voltage. Right? So let's look at the flat band voltage in the MOS capacitor. This is given by phi ms minus QF by Cox. Right? So basically I'm being given two devices with different Cox's and different VFBs. I need to solve for phi ms and QF. So Cox1, that is when T is equal to 50 nanometers, is given by 8.85 into 10 power minus 14 into 3.9 divided by 50 into 10 power minus 7, which is 6.903 into 10 power minus 8 farads per centimeter squared. And if I double my T to 100 nanometers, then essentially my capacitance halves, and so this is 3.4515 into 10 power minus 8 farads per centimeter squared. Right? So I have two conditions here. I have VFP1 is equal to phi ms minus QF by Cox1, and VFP2 is equal to phi ms minus QF by Cox2. And so therefore what do I have? I have QF. If I want to find QF, I subtract the two equations. So I get QF is equal to VFP1 minus VFP2 by 1 by Cox1 minus 1 by Cox2. And substitute that, I get my QF to be 6.9308 into 10 power minus 8 coulombs per centimeter squared. So that is the fixed charge density I have in the system. And once I know QF, I can use any equation here to calculate phi ms, right? And so I can write my phi ms to be minus 2 plus 1, which is minus 1 volt. So the phi ms of the structure is minus 1 volt. So using these two capacitors, I can get information about the quality of the interface and about the work function of the metal that is being used.